Let's look at the K-means clustering, the seventh topic of machine learning. In part 1, we'll look at the basic algorithm of K-means clustering. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. Let's take a look at the full table of contents. In Chapter 1, we will look at the K-means clustering algorithm. Let's take a look at brief history of K-means and look at its training and prediction process. We will then look at the local minimum problem and how to solve it. We cannot fundamentally solve this problem, but we'll look at ways to make it less likely to happen. Finally, we will look at how to define and optimize the loss function for K-means. In Chapter 2, we will look at the K-means plus algorithm, which is designed to reduce the local minimum problem. Let's implement this algorithm from scratch. And let's also implement it using Scikit-Learn's K-means class. Let's cluster MNIST dataset. In Chapter 3, we will look at how to find the optimal number of clusters. Let's look at the elbow method, and then we'll look at the silhouette method. Let's write code that computes the silhouette score from scratch and use it to find the optimal number of clusters, K. Let's look at a brief history of K-means. K-means is an algorithm that clusters similar objects together. Although it is an old algorithm published in the 1950s, it is still widely used today. According to Wikipedia, the term K-means was first used by James McQueen in 1967, though the idea goes back to Hugo Steinhaus in 1956. The standard algorithm was first proposed by Stuart Lloyd of Bell Labs in 1957 as a technique for pulse code modulation, although it was not published as a journal article until 1982. In 1965, Edward W. Forgy published essentially the same method, which is why it is sometimes referred to as the Lloyd-Forgy algorithm. Next, let's look at the training and prediction process of K-means. We want to cluster the data points in the figure on the right into K groups. It seems reasonable to cluster them into 3 groups. We'll see later how many groups we need to cluster them into. But for now, let's consider clustering them into 3. Because it is 2-dimensional data, it is easy to cluster like this by just looking at it. But as the number of features increases, clustering becomes more difficult. So an algorithm is needed. K-means is one of the clustering algorithms. Error cannot be measured in this type of data because it only has features and no target values or labels. Learning from such data is called unsupervised learning. K-means is one of the unsupervised learning algorithms. In supervised learning, the data has target labels or values, y, so the error can be measured as the actual y minus the predicted y hat. We can train a model by minimizing this error. However, in unsupervised learning, the data has no target values, y, so the error cannot be measured directly. We need to measure the error some other way. Now let's look at the training process. In Step 1, K data points are randomly selected and used as K initial centroids, where K is the number of clusters. In the figure below, the 3 initial centroids are like this. This is a centroid initialization process. We then assign data points to their nearest centroid. This data point is close to the centroid 0, so it is assigned to cluster 0. This data point is also close to the centroid 0, so it is also assigned to cluster 0. In this way, every data point is assigned to its cluster. Red data points belong to cluster 0, and blue data points belong to cluster 1. And the green data points belong to cluster 2. This is the data assignment process. Step 2 calculates the average coordinates of these data points. The average coordinates of the red data points are around here, and those of the blue data points are around here. And those of the green data points are around here. Shift the existing centroids to the average coordinates. Those are the new centroids. And then reassign the data points to the new centroids. The red data points are close to centroid 0, so they are newly assigned to cluster 0. These blue data points belong to cluster 1, and green data points belong to cluster 2. Comparing to the figure on the left, you can see that the data assignment has changed. Step 3 repeats step 2 until the centroids no longer shifts. As a result, the centroids are moved towards the center of each cluster. In this figure, you can see that the clustering was done well. This is the update centroids process, and this is the repeat process. Step 4 is the prediction process. Once the training is complete, these centroids are used to predict which cluster the test data point belongs to. The test data point below is predicted to belong to the cluster 0, because it is closest to centroid 0. The sum of the distances between each data point and its centroid can be used as a proxy for training error. The better the clustering, the smaller this error will be. In this figure, we calculate the distances between all red data points and centroid 0, and we calculate the distances between all blue data points and centroid 1. And calculate the distances between all green data points and centroid 2. The sum of the squares of these distances can be defined as the error for K-means. In the initial state, the clustering is not good, so the error increases like this. However, as the iteration progresses, i.e. as the centroids shifts, this error decreases as follows. Repeat step 2 until this error no longer decreases. The final error is 5.67. This is the basic algorithm of K-means clustering. Next, let's look at the local minimum problem. Depending on the randomly set initial centroid locations, K-means clustering may fail, as in the example below. Looking at the results below, you can see that the error decreased with one iteration, but did not decrease further after that. The final error is 17.78, which is larger than the error of 5.67 on the previous page. The locations of the initial centroid are as follows. You can see that the centroids move once through the training process, but can no longer move after that. The reason is that when minimizing the loss function, which is the objective function, it failed to converge to the global minimum and fell to the local minimum. The loss function for KMeans is covered on the next page. To solve this problem, you can try KMeans multiple times while varying the positions of the initial centroid, and choose the result with the smallest error. Although this method is easy to implement, it has the disadvantage of being time-consuming. Another way is to lower the probability of this happening by distributing the initial centroid positions appropriately. This is the KMeans ++ algorithm, and we will look at it in detail later. Next, let's define a loss function for the KMeans clustering and see how to optimize it. KMeans is an algorithm that assigns the data points to each centroid and then minimizes the sum of the squared distances between the data points and their centroids. Step 1 assigns the data points to the nearest centroid, and Step 2 minimizes the sum of the squared distances between each data point and the assigned centroid. In the figure below, there are 4 training data points and 2 initial centroids. These 2 data points are assigned to the first centroid, mu1, and these 2 data points are assigned to the second centroid, mu2. The sum of the squared distances between the data points and their assigned centroids can be expressed as follows. This is the loss function for KMeans clustering. Our goal is to find the coordinates mu of the centroids that minimizes this function, where A is whether to assign or not. The first subscript is the data point number, and the second subscript is the centroid number. The A11 is whether to assign the first data point to the first centroid. Since the first data point is assigned to the first centroid, the A11 is set to 1. Since the first data point is not assigned to the second centroid, the A12 is set to 0. Step 1 assigns data points to each centroid. The assignments, A's, are set as follows. Step 2 finds the coordinates mu of the centroids that minimizes the loss function. Differentiating the loss function with respect to mu k is as follows. When we differentiate it with respect to mu1, all of this part, including mu2, becomes 0. So we only need to use the first sigma symbol. Then the mu k becomes like this. This is the average coordinates of the data points assigned to the centroid k. Therefore, moving the centroid to this location minimizes the loss function. In this figure, it is optimal to move the first centroid to this location, and the second centroid to this location. Like supervised learning, unsupervised learning also allows you to define a loss function and train to minimize it. If A is 0 or 1, it is called hard clustering. And if A is a real value, it is called soft clustering. For example, in soft clustering, if a 1,1 is 0.8 and a 1,2 is 0.2, this means that data point 1 has an 80% chance of being assigned to cluster 1 and a 20% chance of being assigned to cluster 2. In this video, we will only cover the hard clustering. So far, we have seen how KMeans clustering works. In the next video, we will implement this from scratch. We will also implement this using Scikit-Learn's KMeans class and compare the two results.